Hello everyone, welcome back to our class. Let's continue to study Chapter 9, Convection. Section 4, Internal Flow. Last section we have studied external flow. This section we will study internal flow. Flow conditions. Internal flow, most of the case is the working fluid flow in the tube. In the tube flow, we have two terms, two formation flow, laminar flow and turbulent flow. Flow in the tube, if the flow distance is small, we can call it is the entrance region. But if the flow very long distance, we can call it fully developed region. Fully developed region for different flow mode, laminar flow and turbulent flow. Laminar flow, the section like this, but the turbulent flow, the flow section like this is different. Entrance region may be similar because entrance region is very short. It's not so distance. It's not so big the distance. So most of the case we discuss the fully developed region. In laminar flow, the Hx decrease with the x. But in turbulent flow, maybe it's different. At the beginning stage, maybe Hx decrease with the x. But into the turbulent flow, there is suddenly increase, Hx increase, and change very small with x, like this. The curve like this. Okay, experiential relationships. Certainly we can use similar the empiric the relationship to calculate the internal flow heat transfer. In fully developed length, the flow shape must be distinguished laminar or turbulent flow. Reynolds number is an important indicator. If Reynolds number is more than 2,200, it is certainly laminar flow. If the Reynolds number larger than 10,000, it is certainly turbulent flow. If the Reynolds number only larger than 1,200 and smaller than 10,000 in this region is transition region, maybe it's not laminar flow, also it's not turbulent flow. To evaluate the properties with the mean temperature across the pipe. Mean temperature. Because when we calculate the Planck number and Reynolds number, we have to use the temperature. In this case, we use the mean temperature. Also, sometimes for small tube, most of the case we use the average input and the output temperature together. Average. Okay. If the flow is turbulent flow, convection in the tube, how to calculate the Nusselt number? Because this case is very typical, so many scientists do their research for this case. So in this case, we can use very typical the equation to calculate the heat transfer. When Reynolds number equals 10,000 to 1.2 times 10 power fifth. Also, Planck is in the range of 0.7 to 120. In this region, we use the equation Nusselt number equals 0.023 Reynolds number power 0.8 times Planck number power 0.4 and include several coefficients epsilon L, epsilon T, epsilon R, 3 coefficients. This equation is very famous. I hope every student can remember this equation. Okay, we can give more explanation about this equation. The subscript F means the average temperature will be used to calculate the properties. Also, the coefficient epsilon L is a correction factor due to the entry length. Maybe it is enhanced range, maybe it's developed range. So we use this coefficient to do some correction. If L over D larger than 60, epsilon L just is 1, no correction. If L over D smaller than 60, we can do some correction. Epsilon L equals 1 plus D over L power 0.7. This number generally is small, very close to 1, Also, epsilon T is correction factor considering the temperature is not uniform in pipe across. If the pipe is very big in one section, the temperature is not uniform. We can use this factor to do some correction. Generally, epsilon T equals 1. However, when the temperature difference between surface and the bulk of fluid is very big, the coefficient should be considered. Also, another coefficient, epsilon R, is a correction factor about curved pipe influencing on the flow. For example, it's a curved tube, it's not straight tube. For straight pipe, epsilon R is equals 1. Curved pipe for gas, epsilon R equals 1 plus 1.77 times D over R. For liquid, epsilon R equals 1 plus 10.3 times D over R power third. So become big, larger than 1. Okay, for laminar flow in the pipe, when the flow speed is not so fast and the wall of the pipe is it's very smooth. So most case, it is a simple situation, is laminar flow. In this case, Reynolds number smaller than 2,200. For fully developed length, the Nusselt number is a constant, very special, is a constant. If the heat flux is constant, just Qx equals constant. In this case, Nusselt number equals 4.36 is a constant. If in the pipe, the wall, the temperature is constant, just to say Tw is constant in the tube wall, the Nusselt number is another number, 3.66, becomes smaller. So for laminar flow in the tube, the Nusselt number always is a constant. For Qx is constant, Nusselt number is 4.636. For Tw is constant, Nusselt number is 3.66. So this page is very special. For entry length, in entry length, very close to the input. So Reynolds number smaller than 2,200. Also, Reynolds number times Prandtl number times D over L larger than 10. In these conditions, Nusselt number equals 1.86 times Reynolds number plus number times d over L together, power 1/3. We use this equation to calculate. Here, mu W is mean wall temperature to calculate, but mean wall temperature to calculate. Okay, mean velocity we use for tube. If the tube is not so big, we can use the mean velocity to calculate. Because the last page, the Reynolds number, most cases we use the flow rate to calculate. But in the tube, for the tube floor, internal floor, sometimes give the mass flow rate. If the problem is about mass flow rate, in this case, we understand velocity, mean velocity, equals m point over rho A. A is section area. So the Reynolds number, RED, equals 4 times m point over pi rho mu d. We use this equation to calculate the Reynolds number. Flow conditions. When RED is more than 2,300 is laminar flow. If Reynolds number larger than 10,000, it is a turbulent flow. Noticeable. Always we use the average temperature to calculate the Prandtl number, Reynolds number. So T average is T in plus T out over 2. Laminar flow in circular tubes. The total heat transfer rate, certainly from the energy balance equation we obtained, Q equals m point Cp T out minus T in. This equation we can calculate the total heat transfer. In the fully developed region with uniform surface heat flux, Nusselt number is a constant, we know, is 4.36. Here is for uniform heat flux. For laminar flow, fully developed conditions with a constant surface temperature. In this case, Nusselt number equals 3.66. It's very simple. It's a constant. However, for turbulent flow in circular tubes, it's different. In fully developed region, we use this equation to calculate 0.023 RE Reynolds number power 0.8 times Prandtl power n. This equation is very famous. However, when n equals 0.4 for heating, it is by the tube to heating the working fluid, Ts is larger than Tm. We use n is 0.4. However, if it's cooling process, Ts is smaller than Tm. In this case, the n is equals 0.3. Another conditions, we remember this range. All properties evaluated at Tm. Mean temperature. We use mean temperature to calculate all of the properties, all parameters. Thank you.